Today, I would like to present a model for analyzing the effect of handoff control messages on the network capacity. Here is my presentation flow today. I will first talk about the motivations for this work. Next, I will talk about the system model which will be used to analyze the handoff control messages problems. Then, I will analyze how the control message will affect the delay performance of the other normal voice packets. And last, we will have some further discussions and result conclusions. Since the handoff control messages share the same wireless channel with the voice packets, introductions of the handoff control message in the network will increase the workload of the channel. Usually, in order to achieve lower handoff latency, the handoff control message will have a higher priority than the other normal voice packet. So, the voice packets transmitted by the mobile stations may need to be delayed when handoff occurs. In order to improve the performance of the handoff control schemes, we can increase the amount of the handoff control messages. For examples, we can aggressively request the authentications and IP collection setups, or we can start the handoff process on a small received signal difference only. This increase in the handoff control message will affect those delay-sensitive applications like voice over IP. So we want to develop a performance model for investigating the effect of the handoff control message on the delay of the other normal voice packet transmissions. This model will be useful for optimizing the parameters in the handoff control scheme in order to maximize the system capacity and also the handoff successful probability. In the analysis, we will model the system as an MMPP-MMPP1 queuing system as seen by the voice packet. MMPP stands for Markov Modulated Person Process. In this case, that means the arrival events and the service time of the packet will be modeled by two separate Markov chains. For the arrival event, assume there are n identical and independent voice over IP traffic sources. Each of them will be modeled as a Markov chain with two states, on and off. When there are n sources, one of Professor Yu's paper have suggested that the combined arrival stream can be modeled simplest as n plus 1 state MMPP process. The state transition diagram of each of the sources is shown here. Voice packets will be generated at the on state, and the interpacket arrival times will be exponentially distributed. The mean interpacket arrival times will be 1 over lambda. When there is at the off state, there will be no voice packet generated. In our case, we can use this Markov chain to represent the overall packet arrival behavior. The number at each state represents the number of current active voice over IP traffic sources in the system. For example, suppose the current state is at 2. That means there are 2 active sources in the system. When one of them becomes inactive, the system state will change from state 2 to state 1. The rate for this change will be 2 out of, since there are 2 active sources and each of them will have out of to become inactive. Suppose the current system state is 2. There will be n minus 2 inactive voice over IP traffic sources. So when any of them become active, the system state will change from state 2 to state 3. And the transition rate will be n minus 2 times R on, since there are n minus 2 inactive sources, and each of them have R ons to become active. We will also model the server as a Markov chain with two states, on and off. The state transition diagram for the channel is shown here. When it is in the on state, it will serve the voice packets, and the service time is exponentially distributed. When there's handoff request, the server will change to off state, and the processing of the voice packet will be substanted. After the handoff process has finished, the server will change back to on state and start to serve the voice packet again. Study by these authors also shows that the handoff process can be approximated by the person. This justifies our assumption about the handoff message arrivals as a person process. This diagram shows the overall state transitions diagram of the system. In order to specify each state in the system, we will define xy as Q level k as the system state rotations, and the Q level represents the number of voice packets in the system. That means all the state at this column represent one voice packet in the system. X represents the number of current active voice over IP traffic sources, and Y represents whether the server is at the on or at the off state. For examples, this state 3.1 represents there are 3 active voice over IP traffic sources, and the server is at the on state. When there is at least one active voice over IP traffic sources in the system, new voice packet may arrive in the system, and the system Q level will increase. For example, suppose the current system state is 20 at Q level 0. Here, 20 at Q level 0. There will be 2 active sources. When there is new voice packet arrival in the network, the Q level will increase from 0 to 1. Okay, the transition rates for this change will be 2 lambda, since there are currently 2 active voice over IP traffic sources, and each of them have packet arrival rate lambda. Also, if there is packet in the system and the server is at the on state, it will serve the voice packet in the system. For example, suppose the current system state is 1.1 at Q level 1 here. There will be one voice packet in the system, and the server is at the on state. When this packet gets served, the system state will change from 1.1 at Q level 1 to 1.1 at Q level 0, and the transition rate for this change is mu.